Today we'll wrap up this course. It's been a fun journey, but like all journeys, this one too must come to an end. The goal for today's lesson is to tie together some of the big themes we have been discussing and to point to some of the other big ideas out there in the community. We'll start by revisiting the high-level structure of the course. Then we'll go through some of the recurrent patterns and principles we have encountered throughout the course. Finally, we'll talk about some of the broader impacts and applications of knowledge-based AI. Let us revisit the architecture for a cognitive system. We have come across this several times earlier in this course. We can think in terms of three different spaces: a metacognitive space, a deliberative space, and a reactive space. The reactive space directly maps percepts from the environment into actions on the environment. The deliberative space maps the percepts into actions, but the mapping is mediated by reasoning and learning and memory. So while this is a see-act cycle, this is a see-think-act cycle. The metacognitive space monitors the deliberative reasoning, it sees the deliberative reasoning and acts on the deliberative reasoning. As we had discussed earlier, it is better to think of these in terms of overlapping spaces rather than disjoint layers. When we were discussing metacognition, we also saw that we could draw an arrow back from here like this because metacognition could also act on itself. This cognitive system is situated in the world. It is getting many different kinds of input from the world: percepts, signals, goals, communication with other agents. Depending on the input and depending upon the resources available to the agent to address that input, the agent may simply react to the input and give an output in the form of an action to a percept, for example. Or the agent may reason about the input and then decide on an action after consulting memory and perhaps invoking learning and reasoning. In some cases, the input that the agent receives might be as a result of the output it had given to a prior input. For example, it may have received a goal, then come up with a plan, but then it receives the input that the plan failed upon execution. In that case, deliberation can give an alternative plan. A metacognition may wonder about why did the planner fail in the first place and repair the planner, not just the plan. Just like reaction and deliberation are situated in the world outside, metacognition in a way is situated in the world inside. It is acting on a mental world. While deliberation and reaction act on the objects in the external environment, for metacognition, it is the thoughts and the learning and the reasoning that are objects internally in the mental world. Of course, this input is coming constantly. Even now, as you and I are communicating, both you and I are receiving input. And we're giving output as well. In fact, the cognitive system is constantly situated in the world. It is never separate from the world. There is no way to separate it. There is input coming constantly. There is output going out constantly. The world is constantly changing, and the cognitive system is constantly receiving information about the world. It uses its knowledge and its knowledge structures to make sense of the data about the world. And it decides on actions to take on the world. Recall that we had said that intelligence is a function that maps the perceptual history into action. And to some degree, intelligence is about action selection, about selecting the right output to act on the world. Depending on the nature of the input, the output may vary. If the input is a goal, the output might be a plan or an action. If the input is a piece of knowledge, the output might be internal to the cognitive system. The cognitive system may assimilate that knowledge in its internal structures. If the input is a percept, the output might be an action based on that percept. If the input is new information, the cognitive system may learn from the new information and then store the result of the learning in its memory. The world here consists not just of the physical world, but of the social world as well. Thus, this cognitive system is situated not just in the physical world, but is also situated in the social world consisting of other cognitive systems and constantly interacts with them. Once again, the interactions between these cognitive systems can be of many different kinds: percepts, goals, actions, plans, information, data. Any cognitive system is not just monitoring and observing the physical world, it is also monitoring and observing the social world, the actions of other cognitive systems in the world, for example. Any cognitive system learns not just from its own actions, but also from the actions of other cognitive systems around it. Thus, a cognitive system needs to make sense not just of the physical world, but also about the social world. We saw some of this when we were talking about scripts. There we saw how a cognitive system used a script to make sense of the actions of other cognitive systems. This architecture is not merely an architecture for building AI agents. It is also an architecture for reflecting on human cognition. Does this architecture explain large portions of human behavior? We have covered a fairly large number of topics in this course. You may recall this particular chart from the first lesson. Let us go through each one of these circles one by one and see the connections between them. So under fundamentals, we covered knowledge representations like semantic networks. In fact, we used semantic networks to address 2-by-1 matrix problems. Then we covered a series of problem-solving methods. These were very domain-independent general-purpose methods that did not use a lot of knowledge, but were very powerful. Generate and test, mean sense analysis, and problem reduction. Then we turned to production systems that had a specific kind of cognitive architecture. Production systems combine reasoning, learning, and memory. Production systems are both a technology for developing AI agents and a theory of human cognition.
Later we talked about planning. And in order to talk about planning, we first proposed a formal language for discussing plans called formal logic. We learned about the different rules and syntax used for writing formal logical statements, and learned why this is very important, that it allows agents to prove the accuracy of their conclusions based on a set of axioms. That gave us a language that we could then use to talk about planning. And as we found out actually, the origins of planning were in agents making proofs of why a certain set of actions would lead to a certain goal. Here we talked about both partial order planning and hierarchical planning, which are two planning methods that allow agents to make advanced plans for complex tasks, and also allow us to reflect on the way we ourselves plan our actions in a complex environment.
Under common sense reasoning, we covered several important lessons: frames, understanding, common sense reasoning, and scripts. Frames is a structured knowledge representation language that allows us to do understanding. Understanding is such a common everyday activity. We are trying to make sense of the world, but the world is ambiguous. The word take, for example, can have so many different meanings. We saw how frames allow us to disambiguate different meanings of the word take. Under common sense reasoning, we made everyday intuitive inferences about the world around us. While understanding and common sense reasoning were concerned with sentence level understanding, scripts is more concerned about discourse level understanding. Script is an even larger yet structured knowledge representation than frames. It too allows us to make sense of the world around us, both the physical world and the social world. Frames also came up in some of the other lessons. In particular, they came up in the lesson on production systems when we were trying to represent episodic knowledge. They also came up in the lesson on configuration when we were trying to represent plans and the variables of various plans that can take values.
We talked about learning in many lessons throughout this course, but certain lessons were explicitly and solely concerned with learning. We started off by talking about learning by recording cases, where an agent could build up a case library of its own prior experiences to use for future reasoning. That formed the foundation of analogical reasoning as well, that we'll talk about in a second. We also talked about incremental concept learning and version spaces, two different learning methods for learning about information that's coming in incrementally or bit by bit. That was one of our foundational principles of this class that we discussed at the beginning and that we'll revisit in a few minutes. We also talked about classification under learning, which is one of the most ubiquitous problems in AI. We talked about how classification involves grouping large combinations of percepts into equivalence classes to allow for easier action selection. Learning also came up in several other lessons that we did throughout this class, including production systems, case-based reasoning, explanation-based learning, analogical reasoning, and learning by correcting mistakes. Meta-reasoning was also deeply connected to learning, where we could learn from our own experiences by analyzing our own prior thought processes.
As David just said, analogical reasoning is another major topic connected with learning. We talked about learning by recording cases, where we are simply assimilating cases by recording them in a growing case library. As a new problem comes, we use methods like nearest neighbor to retrieve the closest case and invoke that case for the new problem. We talked about case-based reasoning, in which we not only retrieve the case, but we also tweak it or modify it in small ways in order to achieve a new goal. In explanation-based learning, we saw how we could connect instances to concept definitions. We constructed explanations that told us how an instance is an example of a given concept. This involved both abstraction and transfer. We also connected explanation-based learning to creativity. Analogical reasoning made the role of abstraction and transfer even more explicit. We talked about cross-domain analogical transfer, for example, from the solar system to the atomic structure. We saw that one needed rich mental models in order to be able to do analogical transfer. We concluded the lesson on analogical reasoning by connecting it with analogical design or design by analogy. Analogical reasoning, too, is closely connected to creativity.
Our discussion of visuospatial reasoning started with our unit on constraint propagation. Constraint propagation was a very abstract and general way of propagating constraints to make sense of a new situation, and it comes up uniquely in visual reasoning, where we use line labeling to make sense of 3D scenes even if they're presented in 2D, where we use line labeling to make sense of three-dimensional scenes even if they're presented in only 2 dimensions. We also saw how constraint propagation could be used for natural language understanding, and we referenced how we might also use it to understand music or tactile information. Then in visuospatial reasoning, we expanded on these notions to discuss whether it would be possible to reason about the world without extracting propositions. This involved looking at scenes in the world where there was no explicit causality, like a glass that's been spilled on the table. We can infer what happened, but there's nothing in the visual scene that tells us exactly how it arose. Similarly, we also discussed how this could apply to other modalities, like tactile information or musical information.
In the unit of design and creativity, we considered lessons on configuration, diagnosis, design, and creativity. You may recall that in configuration, we were worried about very routine, everyday kind of designs. And we did that kind of design by having a library of plans at different levels of abstraction. We selected a plan at a high level of abstraction, assigned values to some of the variables, and then refined the plan at the next lower level of abstraction. All the components were known. We had to decide on the arrangement of the components in configuration. In diagnosis, we were given data about a malfunctioning system, and we had to identify the fault responsible for that malfunctioning. We took 2 views of diagnosis, classification and abduction. In the classification view, this data was mapped into equivalence classes that acted like hypotheses for this data. In abduction, we composed this elementary hypothesis into a composite hypothesis that could best explain the entire data. Design thinking refers to thinking about problems that are ill-defined and open-ended and under-constrained. In design thinking, the problem and solution often co-evolve. The problem doesn't remain fixed, the solution evolves, but that in turn it leads to improved understanding of the problem. Both our understanding of the problem and the solution evolve together. We characterize creativity in terms of the novelty, value, and the non-obviousness of the results. We discussed the criteria under which we would consider an agent to be creative. And we saw how many of the techniques that we have learned in this particular class can compose the fundamental processes of creativity, like analogical reasoning, like visuospatial reasoning, like meta-reasoning.
Then we closed the class by talking about metacognition. Metacognition enabled agents to reason about their own reasoning, or think about their own thinking, or have knowledge of their own knowledge base. We started off by talking about learning by correcting mistakes, where an agent could look at a mistake it's made in the past, isolate the mistake, explain the mistake, and then fix the mistake so it didn't happen again. This was one narrow instance of the broader idea of meta-reasoning. In meta-reasoning, we talked about how metacognition could bring together many of the different methods that we've talked about throughout this class. Meta-reasoning enabled an agent to look at a new problem and select which of its many strategies would be best for addressing that problem. It also would allow an agent to integrate multiple different methods of reasoning at different levels of abstraction. We also talked about how what meta-reasoning operates is also the way in which meta-reasoning operates. Meta-reasoning can reason about case-based reasoning, or it can reason using case-based reasoning. It could, for example, use production rules to conduct case-based reasoning. In this way, it could integrate many different methods at many different levels of abstraction. Finally, this set up a notion of ethics in artificial intelligence. As we're building AI agents that start to have real human-level intelligence, what are the ethical issues? What should we think about replacing certain human jobs with robots? Or what should we think about developing robots that can interact with us on an everyday basis in the natural world? Under what conditions would we consider these agents to actually be human-like?
This summarizes 30 topics that we covered in this class, which is quite a lot. Of course, there is a lot more to talk about each of these 30 topics than we have covered so far. Therefore, we have provided readings for each of the topics, and you are welcome to pursue the readings for whatever topic that interests you the most. We'll also love to hear about your views about this on the forum. In the beginning of this course, we enumerated 7 major principles of knowledge-based AI agents that we'll cover in CS7637. Let us wrap up this course by revisiting each of the 7 principles. Here is the first one. Knowledge-based AI agents represent and organize knowledge into knowledge structures to guide and support reasoning. So the basic paradigm here is represent and reason. Represent and reason. If you want to reason about the world, you have to represent knowledge about the world in some way. You not only want to represent this knowledge to support reasoning, you also want to organize this knowledge into knowledge structures to guide, to focus the reasoning. Let us look at a few examples that we covered in this course about this principle. Semantic networks not only allow us to represent knowledge about the world, they also allow us to organize that knowledge in the form of a network. We use semantic networks to address the problem of the guards and prisoners dilemma. The advantage of the semantic networks was that they exposed the constraints of this problem so clearly so that we could in fact reason about it. And notice that the organization helps us focus the reasoning. Because of the organization, there's so many other choices, we don't even have to reason about them. Frames were another knowledge structure that organized knowledge and guided and supported reasoning. Given frames for things like earthquakes, we could reason about sentences like a serious earthquake killed 25 people in a particular country. We also use frames to support common sense reasoning. Here Ashok is moving its body part to a sitting position. Here Ashok is moving himself into a sitting position. Here Andrew sees Ashok. Now Andrew moves to the same place as Ashok, and Andrew then moves the menu to Ashok. This is about a story about visiting a restaurant. Once again, there is knowledge structures here. And these knowledge structures are not only representing knowledge, they're organizing knowledge into a sequence of actions. These knowledge structures help generate expectations. So we know what Ashok expects to happen next in any of these situations. We also know how Ashok can detect surprises. When the non-obvious thing happens, Ashok knows it has violated the expectations of the scripts and can do something about it. This is how the scripts support and guide reasoning. We also saw this principle in action when we were talking about explanation-based learning. In order to show that an instance was an example of a particular concept, cup, we constructed complex explanations. In this case, we were constructing the complex knowledge structure on the fly out of smaller knowledge structures. The smallest knowledge structures came out of precedents or examples we had already known. And then we composed the knowledge of these various knowledge structures into a complex explanation to do our reasoning, to guide and support the reasoning. We have seen this principle in action in several other places in this course. This is one of the fundamental principles: represent, organize, reason.
Our second main principle for CS7637 was that learning in KPAI agents is often incremental. This means information or data or experiences arrive one at a time. This is one of the key differences between knowledge-based AI and other forms of AI like machine learning. In those forms, a large amount of information is often given right at the beginning. Here, our agents learn step by step, incrementally. We first encountered this with learning by recording cases. Our agents learned each individual case one by one. The experiences themselves were the increments in this learning strategy. Case-based reasoning also operated on individual cases, but it organized them into much more complex knowledge structures, like tagging them in an array, or organizing them by a discrimination tree. But the fundamental object of knowledge were still individual cases that arrived one by one. We did a complex exercise where one by one we added these new cases into our discrimination tree. Incremental concept learning was, as the title suggests, incremental. Here we received positive and negative examples one at a time. Based on the difference between our current concept and our new example, and whether or not the new example was a positive or negative example, we would change our concept. This was always done example by example, incrementally. Version spaces involved a very similar kind of knowledge. Here, experiences came one at a time, and we generalized a specific model and specialized the general model to converge down to an understanding of the concept. Finally, learning by correcting mistakes was also deeply incremental. Here, the individual mistakes arrived incrementally, and based on the individual mistakes, our agent modified its knowledge base to repair the cause of the previous mistake. The takeaway here is that many of our methods in learning, reasoning, and memory all involve dealing with information that comes incrementally, bit by bit, instead of processing a large amount of data all at the same time. One can also see that this connects more closely to human experience, where we're constantly experiencing the world, experience by experience, instead of being given a lifetime of experiences all at once.
The third principle of knowledge-based AI agents in CS7637 is that reasoning is typically top-down as well as bottom-up. Ordinarily, we assume that data is coming from the world and most of the reasoning is bottom-up as we interpret the data. In contrast to knowledge-based AI, low-level processing of the data results in the invocation of knowledge structures from memory. These knowledge structures then generate expectations and the reasoning becomes top-down. Frames were an example of this kind of top-down reasoning. We had the input, Angela ate lasagna with her dad last night at Olive Garden, and the processing of this input led it to the invocation of this particular frame. Once this frame has been pulled out of memory, then this particular frame can generate a lot of expectations. For example, was the object alive when Angela ate it? False. Where is the object now? Inside the subject. What is the subject's mood after she had dinner? She was happy. A similar kind of top-down generation of expectations occurred when we used frames to understand simple sentences about earthquakes. Scripts were another example of this kind of top-down generation of expectations and expectation-based processing. Once we have a script, then the script generates expectations about the next action. It tells us what to look for in the world even before that happens. And when that doesn't happen, we know an expectation has been violated and we are surprised. Constraint propagation is another way of thinking about top-down processing. We have input data in the form of pixels representing this cube. We have to infer that this image in fact is that of a cube. We have knowledge about these constraints of various kinds of junctions that can occur in the world of cubes, and this knowledge then generates expectations of what might be a blade and what might be a fold. This notion of top-down processing, using knowledge structures to generate expectations of the world in order to be able to interpret data, is central to knowledge-based AI. It's also deeply connected with human cognition. Some current theories of human cognition think of brains as predictive machines. We are constantly generating expectations. We are constantly making predictions about the world that guide our reasoning, that guide our actions.
Our fourth principle was that knowledge-based AI agents match methods to tasks. At the beginning of this course, we covered several very powerful problem-solving methods like generate and test and means-ends analysis. But because they were very powerful and very general, they also weren't necessarily the best for solving any one problem. We also covered some more specific problem-solving methods like planning that addressed a narrower set of problems but addressed those problems very, very well. We also covered several tasks in this class like configuration and diagnosis and design. These tasks could all be carried out by a variety of methods. For example, we can imagine doing configuration with generate and test, where we generate every possible configuration of a certain plan and then test to see which one's best. We could also do configuration by problem reduction, where we reduce the problem down to the subparts and solve them individually and then compose them into an overall solution. In this way, knowledge-based AI agents match methods to tasks. In some cases, we do the matching. We decide that generate and test is the best way to address this diagnosis problem. In other cases, we might design AI agents with their own meta-reasoning, such that they themselves can decide which method is best for the task that they're facing right now. Note that this distinction between methods and tasks is not always necessarily absolute. Methods can spawn different subtasks. So for example, if we're doing design by case-based reasoning, that spawns new problems to address. And we might address those new problems, those new tasks, with analogical reasoning or with problem reduction. This gets back to our meta-reasoning notion of strategy integration. In this way, knowledge-based AI agents match methods to tasks not only at the top level, but also at every level of the task-subtask hierarchy.
The fifth principle of knowledge-based AI, as we have discussed it in CS7637, is that AI agents use heuristics to find solutions that are good enough, though not necessarily optimal. Some schools of AI put a lot of emphasis on finding the optimal solution to every problem. In knowledge-based AI, we consider agents that find solutions that are good enough. Herbert Simon called this satisficing. The reason for finding solutions that are only good enough is because of a trade-off between computational efficiency on one hand and optimality of solutions on the other. We can find optimal solutions, but that comes at the cost of computational efficiency. Recall one of the conundrums of AI. AI agents have only limited resources, bounded rationality, limited processing power, limited memory size. Yet, most interesting AI problems are computationally intractable. How can we get AI agents to solve intractable problems with limited rationality and yet give near real-time performance? We can get AI agents to do that if we focus on finding solutions that are good enough, though not necessarily optimal. Most of the time, you and I as human agents do not find optimal solutions. The plan you may have to make dinner for yourself tonight is not necessarily optimal. It's just good enough. The plan that you have to go from your house to your office is not necessarily optimal. It's just good enough. The plan that you have to walk from your car to your office is not necessarily optimal. It's just good enough. Further, AI agents use heuristics to find solutions that are good enough. They do not do an exhaustive search, even though exhaustive search might yield more optimal solutions, because exhaustive search is computationally costly. We came across this notion of heuristic search several times in this course. One place where we discussed this in some detail was in incremental concept learning. Given a current concept definition and a negative example, we arrived at a new concept definition by using heuristics like the required link heuristic. The required link heuristic adds the must clause to the support link between these two bricks. Mean sense analysis was a heuristic method. It said that, given the current position and the goal position, find the differences and then select an operator that will reduce the difference. Because mean sense analysis was a heuristic method, sometimes it ran into problems and did not provide guarantees of optimality. But when it worked, it was very efficient. Another place where we explicitly made use of heuristics was in the generate and test method. Here we had a heuristic which said, do not generate a state that duplicates a previously generated state, which made the method more efficient. Thus, the focus of knowledge-based AI agents is on near real-time performance and addressing computationally intractable problems with bounded resources, and yet being able to solve a very large class of problems in robust intelligence and flexible intelligence. And that happens not by finding optimal solutions to a narrow class of problems, but by using heuristics to find solutions that are good enough to very large classes of problems. This principle comes very much from theories of human cognition. As I mentioned earlier, humans do not normally find optimal solutions for every problem they face. However, we do manage to find solutions that are good enough, and we do so in near real time, and that's where the power lies.
Our sixth principle was that knowledge-based AI agents make use of recurring patterns in the problems that they solve. These agents are likely to see similar problems over and over again, and make use of the underlying patterns behind these similar problems to solve them more easily. We talked about this first with learning by recording cases. Here we assumed that we had a library of cases and that the solution to a former case would be the exact solution to a new problem. Ashok's example of tying shoelaces was similar to this. When we tie our shoelaces, we aren't resolving the problem of tying our shoelaces from scratch. Instead, we're just taking the solution from an earlier time when we tied our shoelaces and doing it again. We assume that the solution to the old problem will solve this new similar problem. In case-based reasoning, however, we talked about how the exact solution to an old problem won't always solve new problems. Instead, sometimes we have to adapt an old problem. Here we assumed that there were recurring patterns in the world that would help us solve these new and novel problems based on previous experiences. Even though the new experience is novel, the pattern is similar to a prior experience. Analogical reasoning is very deeply rooted in this principle. Here we explicitly talked about the idea of taking patterns from one problem, abstracting them, and transferring them to a problem in a different domain. Whereas in case-based reasoning, the pattern was within a domain, here the pattern can span different domains. In configuration, we assumed that the underlying design, the underlying plan for a certain device or product, was pretty similar each time, but there were certain variables that had to be defined for an individual instance of that object. In the chair example, the overall design of a chair is a recurring problem. They all have legs, they all have seats, they all have backs, but the individual details of a specific chair might differ. Now, it might be tempting to think that this is actually at odds with the previous principle, that knowledge-based AI agents can solve novel problems. Here we're saying that knowledge-based AI agents solve recurring problems based on recurring patterns. But in fact, these are not mutually exclusive. Knowledge-based AI agents leverage recurring patterns in the world, but they do so in conjunction with other reasoning methods to allow them to also address novel problems.
So the seventh and last principle of knowledge-based AI agents in CS7637 is that the architecture of knowledge-based AI agents enables reasoning, learning, and memory to support and constrain each other. Instead of building a theory of reasoning or problem-solving by itself, or a theory of learning by itself, or a theory of memory by itself, we have tried to build unified theories, theories where reasoning, learning, and memory coexist. Memory stores and organizes knowledge. Learning acquires knowledge. Reasoning uses knowledge. Knowledge is the glue between these three. One place where we saw reasoning, learning, and memory coming together very well was in production systems. When reasoning failed and an impasse was reached, then memory provided some episodic knowledge, and the learning mechanism of chunking extracted a rule from that episodic knowledge, and that rule broke the impasse and reasoning could proceed apace. This was a clear example where reasoning, learning, and memory came together in a unified architecture. In logic, memory, or the knowledge base, may begin with a set of axioms, and those set of axioms decide what we can prove using that particular logic. To look at the problem conversely, depending upon the reasoning, we need to put things in the knowledge base so that the reasoning can be supported. Explanation-based learning was another place where reasoning, learning, and memory came together so well. Memory supplied us with the earlier precedents. Reasoning led to the composition of this explanation, which explained why an instance was an example of a cup. This led to learning about the connections between these various precedents into an explanation. Learning by correcting mistakes was yet another example of learning, reasoning, and memory coming together. When a failure occurred, then the agent used its previous knowledge, memory, to reason and identify the fault responsible for the failure, reasoning, and then corrected that particular fault, learning, in order to get the correct knowledge. Thus, the knowledge-based paradigm says that we want to build theories that are unified, that connect reasoning, learning, and memory. And this also connects very well with human cognition. Human cognition, of course, has reasoning, learning, and memory intertwined together. It is not as if memory and human cognition works by itself, or learning works by itself, or reasoning works by itself. You cannot divorce them from each other. Knowledge-based AI is a dynamic field with a very active research program. There are a number of exciting projects going on right now. Here is a small list of them. Callow is a project in which a cognitive assistant learns and organizes knowledge. Callow, in fact, was a precursor for the Siri program of Apple. Psych and OMCS. OMCS stands for Open Mind, Common Sense. Psych and OMCS are two large knowledge bases to support everyday common sense reasoning. Wolfram Alpha is a new kind of search engine that uses some of the same kind of knowledge structures we have considered in this particular class, different from many other search engines. The three projects in the right column are projects here at Georgia Tech. Vita is a computational model of visual thinking and autism. In particular, it solves problems on the Raven progressive matrix test using only visuospatial representations. Dramatis is a computational model of suspense in drama and stories. Recall that in this class we talked about a theory of humor and surprise. Dramatis tries to do the same thing for suspense. Data is a system for supporting design based on analogies to natural systems. We had come across this idea of biologically inspired design earlier in the class, and Dane supports that kind of biologically inspired design. We have provided references to these and many other knowledge-based AI projects in the class notes. You are welcome to explore depending on your interests. This brings us to the end of the course. There are many more topics that we could talk about, and we encourage you to look at the additional readings for the course. As we said at the beginning, we have had a lot of fun putting this course together, and we have learned a lot too. We hope you have enjoyed the course as well.
We're also really eager to get your feedback. What did you enjoy about this course, and what could have been improved? What surprised you about this course, either in the content or in the way it was administered? Are there things you've seen other courses do that you wish we had done? Or are there things that we did that you'd like to see other courses do?
We are very interested in your answers to these questions. So please feel free to contact either one of us with your answers and fill out the course survey as well.
We'd also like to thank several people for helping make this course possible. First, our video editor, Aaron, who's done a phenomenal job making these videos look so good and frankly making us look presentable. We'd also like to thank the rest of Udacity, especially Jenny Kim, Jason Barros, and Katie Reichelt, for providing a great infrastructure for course development.
We'd also like to thank our colleagues here at Georgia Tech, including David White and the College of Computing, and Mark Weston and the staff of the Georgia Tech Professional Education Department. It's been a real fun journey for us. We expect to hear from you. We hope it's the beginning of a beautiful friendship.